Welcome, ladies and gentlemen, to our conversation on accuracy, precision, and percent error. Be sure to double check your table of contents that includes your objectives to confirm which objectives this aligns with. Now, in chemistry, we do quite a bit of measurement, especially looking at masses and volumes as we're working with different types of substances. So it's important to distinguish the difference between the accuracy of a measurement and its precision. Accuracy is another way of saying that you are right. So think about hitting the bullseye in one of these targets. If you're an archer and you hit the bullseye, you are accurate with that shot. Now, if you are precise, it's a little bit different. Precision is more about consistency. So you could be precise but not accurate. You could also be accurate but not have a lot of precision. So in our first archer target, our bullseye, we'll take a look at accurate but not precise. They're around the bullseye, but they're not really in the same area, and they're kind of all over that center area. Now the second one, we'll look at precise. Maybe the archer is setting up with their sight line a little bit off to the left. Maybe their footing is off. They're very consistent. We're seeing that all of the targets are falling into the same spot, but they are not hitting an accurate part. Accurate and precise is the goal of our work this year. So as we look through our data, one of the ways that we are able to make sure we correctly report precision in our measurements is by how we report the digits in our data. So we are going to be limited by the tools that we use. So you can't put in a whole bunch of decimal places just because the calculator tells you that's the case. We have to work with the materials that we have available to us. Now, percent error is a way for us to be able to be precise and accurate, but then assess the accuracy of our work. So percent error is a way to account for the error in our measurement and know how close we were to the expected value. So one thing I want us to practice is we've just introduced this idea of accurate versus precise, and I want you to decide if it's accurate only, precise only, both, or neither. The measurement we were trying to measure was 68.1 milliliters. So as you look at these sets of data, take a moment and then pause the video and go through and make your decisions. I'll give you a couple seconds on my end, should be a few more than that on your end, and then I will provide the answers. Now the first one has one value that's somewhat close to the correct measurement, but they're kind of all over the place, so I don't know if they were using the wrong one or just not paying attention, but that's neither. Really struggling to spell today. Next set is very consistent. They're all within like 0.1 of each other, 0.2, and they're all right around the correct one. So that one is both. The next one, the values are all very close to each other, but there must be some kind of error in the reading of the values. So in this case, it's very precise, but it's not accurate. The last set, if you look at it, they're pretty close. If you average them out, we would get an average pretty close to 68.1, but they're not close to each other. So whatever error is going on here, it's not an error of consistency. So sometimes it's really hard to be accurate. without being precise, but when we're doing multiple trials of a procedure, any variation in your procedure can introduce that inconsistency. So if we want to know how close our answer is to the real answer, we can do a percent error calculation to evaluate that accuracy. Again, it's a measure of how far we were from the expected value. So error alone is the absolute value of the experimental minus the accepted. If we then take that and divide by the accepted, we will get percent error. So error is something that will be specific to the values that you get. Percent error makes that comparable against all kinds of different trials. Notice that it is absolute value. So at this point, we don't care which direction you were off in this value. We just want to know the relative amount you were off. So that's why it doesn't matter the sign. So let's take a look at a sample problem for percent error, and we're going to use our analyze the prompt strategy for it. So a student measured the string as 1.25 meters long. The teacher said it was actually 2.12 meters long. What was the percent error of the student? So here I boxed my variables. We have an experimental value and an actual value. And then I'm going to box and star percent error. So the next thing I'm going to do is write out my equation. Now that I know my plan, I'm going to implement the plan and plug in my variables. Notice that I almost forgot my times 100 in there. Make sure that you guys take care of that and put that in even in your own work. When we get that all set to go and we punch that in the calculator with my absolute value, I get 41%. Now, just a little thing to notice, while I said that we don't care about what direction it is, there's an interesting connection here. You'll notice that the experimental was less than the actual. And with this version of the equation, you actually get a negative percent. So a negative sign in this case does mean that it is less than the actual. When you guys are reporting your final values, though, I only need the positive value. That tells us this measurement was pretty far off and not very accurate. Under ideal conditions, we're aiming for 5% or less. In our lab conditions, 10 or less is fairly reasonable. Next problem we'll annotate together, and then it will be your responsibility to do the rest of the problems on your own. So you guys will be responsible for knowing the percent error equation. You will have to be able to then apply it on assessments as well. So this equation will not be provided to you. When you come to class, make sure you are prepared with questions on any of the problems that you are required to do.